Hello, my name is Lachlan, and today I'm going to be introducing you to the concept of partitions, which are a fundamental and quite enjoyable area in combinatorics. Now, the most natural way, I believe, to be introduced to partitions is in the form of a question like this. So, how many different ways can we add natural numbers together to achieve a total of 6? Obviously, I've written here 3 plus 2 plus 1 equals 6. However, there are in fact 11 different ways to achieve this result. Okay, so the answer to our question is 11. And we could also phrase the same question by instead saying, what is the partition number of 6? That is to say, how many different ways can we partition 6? Now, a more useful way to instead write these partitions is in the form of these sequences. So here I've written the sequence 3, 2, 1 to encode that sum from before of 3 plus 2 plus 1. And because that sum on the right equals 6, we say that that sequence on the left is a partition of 6. More generally, partitions are weakly decreasing sequences of non-negative integers whose terms form a finite sum. So for example, we can add 1, 2, or a tail of infinitely many zeros to a partition, and we in fact say that it is the same partition. You'll also see that you're going to get frequently a lot of repetition. For instance, in this example here, 1 occurs 3 times. Rather than writing 1 3 times, you can write 1 raised to the power of 3. That is to say that the multiplicity of 1 in that partition is equal to 3, or 1 occurs 3 times in that partition. Now, some non-examples here. You cannot permute a partition. That results in what you would refer to as a composition. You also cannot have an infinite tail of 1s, for example, because then the sum is no longer going to be finite. So here you can see I've written partitions on the left, weakly decreasing sequences, right? Non-negative integers, and they all sum to 6, so their sum is finite, right? And those partitions encode the same summations as before, which are still on the right. Now, a very useful concept when working with partitions is what you refer to as the shape of a partition, or its Young diagram. And the way that you do it is as follows here. Take that same partition from before, 3, 2, 1. The first element of the sequence is 3, so I begin with a row of 3 boxes. Second element was 2, so directly under that I place a row of 2 boxes. The last element was 1, so as the third and final row I place an element of 1 box. And if you would like, remember, you can imagine an infinite tail of no boxes, right, which would be an infinite tail of zeros going below. Similarly here, I have the shape or the Young diagram for the partition 2, 2, 1, 1 and the partition for 2. Now, the partition 2, 2, 1, 1 and the partition for 2 are what we refer to as conjugate partitions. This is because interchanging the rows and columns of their Young diagrams will flip back and forth between each other. Now, you could also, instead of thinking of it interchanging rows and columns, I find it's more easy to visualize if I just imagine a downward diagonal going through the top left cell, and I reflect over that diagonal. You can also see that the leftmost partition, 3, 2, 1, is in fact self-conjugate, because it going through that downward diagonal through the top left cell and reflecting back and forth across it, I'm going to get the same shape, so it is in fact self-conjugate. Now, something really nice we can do here, I can take those 2 conjugate partitions from the previous slide, right? The partition for 2 and the partition 2, 2, 1, 1. And if I write out that same list I had before in what you would call lexicographical ordering, and I go the same number from the front and, from the beginning and the end of the list, right? That's where I'll see my conjugate partitions. And this in fact repeats. So you can see that the conjugate partition of 6 is a sequence of 6 1s, right? And what we have here is that self-conjugate partition of 6 occurs in the center of the list in that lexicographical ordering. And what this tells you is a rather nice way of seeing it, that in order for a number to have a self-conjugate partition, the partition number of that number, which in this example is 6, that partition number must be odd. So here, the partition number of 6 is 11, so we have got that one self-conjugate partition sitting in the middle. And I think this is just a rather fun result. That's quite nice to see. Anyway, thank you.